Hello and welcome to another Cashmatics video. This is another video in the series of videos I'm doing for integration, and in this one in particular we're going to be looking at using the reverse chain rule to integrate functions. Now I'm going to do this in two parts, and this part will be the easier of the two because we're looking at quite a straightforward rule. But in order to demonstrate it, we're going to have to look at some differentiation first. So grab yourself some paper and a pen and we'll get started. Right, so as you see on the screen, we've got three different functions, but they're all log functions or natural log functions. And what we're going to do is we're just going to differentiate these using the chain rule. So let's look at the first one here. We've got y equals ln x squared plus 1. So whenever you're differentiating an ln function, it becomes 1 over the function, but then we have to remember to multiply by the derivative of what's inside the brackets. So in the first case, we get dy by dx is equal to 1 over x squared plus 1 multiplied by the derivative of this, which is 2x. Okay, so we end up with 2x over x squared plus 1. In the second one here, we do pretty much the same thing. We do dy by dx equals 1 over x cubed plus 2x multiplied by the derivative of what's in the brackets, so 3x squared plus 2. So let's just tidy that up a little bit. That's 3x squared plus 2 over x cubed plus 2x. And the last one's done in exactly the same way. So dy by dx is equal to 1 over sine x multiplied by cos x. So that's cos x over sine x. Now in each of these cases, what you need to note is if the bottom is f of x, the top is f dash x. Okay, it's the derivative of the bottom. Okay, so you've got f of x over here and you've got f dash x there. Okay, and that happens in all of these. So what we can conclude from this is that if my integral is in the form where the top is the derivative of the bottom, or if using more mathematical terms, if the numerator is the derivative of the denominator, then the integral will just be the natural log of the denominator. Okay, so that's the simplest case scenario when it comes to these reverse chain rule questions. So the top is the exact derivative of the bottom. So we'll do a few examples where we can see this is in play. This is the case, and then we'll do some slightly tricky ones where we'll have to tweak the final answer to get the result we need. So this is the first example. If you look at the bottom, we've got x cubed plus x, and if I was to differentiate that, I get 3x squared plus 1. So the top is the exact derivative of the bottom. So when I integrate this, it's as simple as just writing the natural log of the bottom plus c. It's really as straightforward as that, but you need to recognize and look for the fact that the top is the derivative of the bottom. Okay, you might not always spot it, so you need to make sure you're looking out for it. In this second example, it looks horrible, but if you were to look at it carefully, again the top is the exact derivative of the bottom. Okay, so e to the 2x plus x squared. E to the 2x, when I differentiate it, becomes e to the 2x multiplied by 2, so 2e to the 2x, and x squared becomes 2x. So again, just like the question before, what I've got as the integral is e to the 2x plus x squared and c. Right, in this third example, again, the same thing's happening. The top is the derivative of the bottom, so it's going to be ln sine x plus c. Now this is actually an interesting one, because quite often you'll see this written as the integral of cot x dx, and people often get stuck. They don't know what to do with cot x. But if you were to split it up as cos x over sine x, then you can apply the rule for integrating using the reverse chain rule. In this next example, we've got a slight problem. The top isn't the exact derivative of the bottom. So let me show you what I mean. If that's f of x, so f of x is x squared plus e to the x, the derivative f dash x would be 2x plus e to the x. Okay, so it's not quite, so this isn't quite what I've got here. Okay, what it is, what I've actually got at the top there is 3 times this. And what that means is, in my integral, I need to introduce the 3 in order to make the correct answer. So it's done just like before. I've got ln of x squared plus e to the x, add c, but that's not going to give me the right answer. That's not going to give me the answer I'm looking for. Okay, what I need to make sure I do is include a 3 in order to get the correct answer. Let me just write that a little bit neater. 3 ln of x squared plus e to the x. So let's just test this. Okay, so now if I was to differentiate this now, it'd be 3 over x squared plus e to the x multiplied by 2x plus e to the x. And if I was to multiply this by 3, I'd get the right numerator. So what you've got to make sure of is that you consider the ln of the bottom, so the natural log of the bottom, differentiate to see what you'd get, and if you need to, introduce another factor to get the correct answer. Okay, and one last example. So again, we've got the same issue we had last time. The top isn't the derivative of the bottom. It's a multiple of it. Okay, it's 7e to the x. So what I need to do is consider the derivative of this. Okay, because if I was to differentiate this, I would get 1 over e to the x plus 4 multiplied by e to the x. Okay, so it's not quite what this is. So what I need to do is make sure I include that 7. So if I multiply this by 7, I'll get the correct answer. And don't forget your constant of integration. And to write that a little bit neater, it'll be 7 ln e to the x plus 4, add c. So I hope that's helped you with this first part of the chain rule. It is quite straightforward. And when we come to the next part of the tutorial, in part 2, you'll see that sometimes things look like you might have to use this chain rule, but that isn't actually the case. Sometimes there's a different type of chain rule we need to consider. So don't get the two confused, and you'll see what I mean once I start the second video. So that's all for now, and I'll see you next time. Goodbye.